Started with our next course. Well, good morning, everyone. Here we are. I think this is where we left off. Here. And, we've only really looked at two curves so far beyond the conics. The Greeks certainly were experts in straight lines and circles. That's what Euclid's Elements are all about. And with Apollonius, we come to their master treatise on the conics. But we've only seen two other curves other than those. That was the triactrix, and Archimedes is spiral. This is another one that I have to show you, another curve which is not a conic, something which is beyond that. There aren't that many in Greek geometry beyond the conics. One reason is because, every curve has to be given this complex locus definition, and they're involved, they're written in words, and they have to make sense. Once, of course, we move to analytic geometry, we can just write down any old equation we like.
Peter, okay, you are freezing and breaking up.
Okay. Oh, I don't know what to do. What we can do is we can turn off our videos, and I can turn off my video.
You're back now.
I'm back now. All right, Mike, interrupt me again if that happens again. And I've just enabled the transcript. And okay. So
Peter, I lost you just after you mentioned Apollonius. You were
okay,
saying
let me repeat that. What I was saying is I'm about to show you a curve that is not a straight line or a circle, and is not a conic section, an ellipse, a parabola, a hyperbola. And there aren't that many of these curves in Greek geometry. It wasn't easy to create curves the way they did them, because they had to describe them with a locus. Remember, for example, the locus of a parabola is defined using an axis and the directrix and how far away the point is from those things. It's a rather complex definition. Here I have another complex definition, and I'd like to show you this curve, but to remind you that there's a reason why there weren't that many curves studied by the Greeks beyond the conics, because they are not easy to define. So let's go ahead and take a look at this locus. We start with two curves very generally. We'll pick the simplest ones, a circle and a straight line. We'll have the straight line tangent to the circle, as you see, and we take the point O on the circle, the exact opposite from the tangent point. And I'm going to describe a locus. Let's go ahead and draw a line from O through the two curves, through the circle and through the straight line. And we'll notice where it crosses the circle and the straight line. This arbitrary line that I've drawn from O crosses the circle at C and the straight line at T. I go ahead and notice that distance. I take a look at that distance CT, and I measure it off from O. I measure the very difference CT, that distance from O, and I mark a point. That's the locus of this point. It's called the sysioid. And this particular definition was used by a man by the name of Diocles. And so this curve that I'm about to show you is called the sysioid of Diocles. Let's take another point, get the idea of this. Again, we draw an arbitrary line from O that crosses the two curves, the circle and the straight line. And we notice the distance between the circle and the straight line created by that particular line from O. We take that distance and measure it again from O, and we mark another point. And that's how the points of the sysioid are defined. You have to admit, much more complicated than the locus of a circle, which is simply the locus of all the points equidistant from the point O. This is a much more involved locus, but a very interesting one, because it gives us this curve, the sysioid of Diocles. Diocles was again a younger contemporary of Apollonius. So we have this kind of progression of mathematicians in Alexandria from Archimedes to Apollonius and now to Diocles, a younger man who probably knew Apollonius. So here's our curve, and let me give you the animation of it. Remember that the locus is given as a definition point by point. Our animations really are, a stretch. They're an anachronism. They didn't really think of this in this kind of a continuous way, but it is nice for us to see it to get a better idea of what the curve is doing. So here is our curve. Let's just run the animation first. And we're watching the red point here as it turns out the cissioid. And for example, here we have the distance from the circle to the line. We take that distance and measure it from the point O, and it creates a point. We take another point, another line here. This line is now longer. This is line here from the circle to the straight line. We take this long line and measure it from here. It goes all the way out to here. There's an overlap because the line is so long. And so there we have it, the cissioid of Diocles. Like I said, there aren't that many. There's really almost a handful of these kinds of curves beyond the conic and beyond the spiral of Archimedes. So they're kind of rare. And they were very important to our mathematicians of the 17th century. As they developed their analytic geometry and as they developed their calculus, they went back to these very precious curves, and they tried to find the area under them. They tried to find the tangents at any point. They tried to find the arc length, the length of these circles. They went back to these historic curves, and first of all, tried to write them in equations, to try to write them in analytic geometry, and then apply their new mathematics to them. And that's why they have lived on. These were the early examples that the mathematicians turned to. They said, I have this new tool of analytic geometry. Let me take that locus, that verbal locus of Diocles, and see if I can translate this into my new platform of an equation. Let's go back to our. So here is our curve, and Diocles proves a very interesting property about this curve. You might ask, where does he come up with this locus, this complex locus? Well, he's trying to actually solve the Delinean problem. He's actually trying to find the cube root of 2. He's actually trying to find that double proportion. That little equation that we showed back in the first, back in the previous presentation, to show, from the double proportion, the mean proportional between 1 and 2 would be the cube root of 2. The cissioid of Diocles accomplishes this quite remarkably, and let me show you. What he proves is a more general theorem. He says, take any point B on that line going through O, and take this length OB. Remember, to the Greeks, all numbers were lengths. All square numbers were areas. So we have this length OB. Its construction is, once we have B, draw the line from B down to the tangent point of the straight line on the circle A. Well, this line here from B to A, of course, will cross the cissioid at some point. Okay. Take that point and draw the line through the cissioid. Go back to O, find the intersection from B to A of the point, and then draw the locus point through this point here, and we'll get another point on the straight line C. Kind of complicated. Let's go back and do it again. Okay. We start with any point B, pick any point along this line. Okay. Draw the line from A to B, right? O and A are fixed points. They're part of the locus. We take an arbitrary point B and draw the line AB. We notice where it crosses the locus of our cissioid. We take that point and draw the line from O through that point and allow it to hit the tangent line again at C. Diocles proves a remarkable theorem. He proves that AC is the cube root of OB. Think of that. Very generally, he proves that AC, this constructed point from the arbitrary point B, he proves that AC is the cube root of OB. And of course, if we let OB equal 2, which we're particularly interested in solving the Delineant problem, then AC will be the cube root of 2. And remember, that was the problem, right? The problem was to double the volume of the cube. If the volume of our original cube was 1, then to get a volume of 2, we need the cube root of 2, because the volume is the length times the width times the height. So the cube root of 2 times the cube root of 2 is the cube root of 2 is 2. So we're looking for the cube root of 2 to solve that problem of doubling the cube of that alter. So that's why he was looking for the cube root of 2, and he invents this locus to solve that problem. Incredibly creative. And I say that the curve is beyond the conics. This is not a conic section. Okay, this is something quite different. And so let me show you the animation of how general this construction of Diocles is. Here we'll take any point. Okay, here's our points. Remember, the construction is take any point you like along that line here, draw the line back over to what we called A. Here's B, here's A. It crosses the cissioid at some place, and then go back to O and draw the line through that intersection point and let it hit the tangent line. Okay. What he proves is that this line here is this length of this line is the cube root of this line here. And I'm showing the numbers here. Here we have the number 1/2 in black. The construction shows the length of this line here, which I claimed, Diocles claims is the cube root of 1/2, which is 0.7937. And if someone has a calculator, by the way, we're going to play with the calculator a bit today. If someone has a calculator and can take cube roots on their calculator, they can check this. We can go ahead and to our simplest point, the simplest point of 1. Okay, according to this construction, if you take the length 1, we draw the line back to the tangent point, see where that line crosses the cissioid here, and then draw the line up through that intersection through the cissioid, and you will get this other point. Well, certainly the cube root of 1 is 1. Okay. But this works for any point. Any point there on B, as it moves up and down, this construction is being done over and over again, and that this red line here is calculating the cube root. And finally, the last one I've translated up here at 2. And indeed, the cube root of 2 is 1.2599. Okay, so it's a very incredible construction being done at 150 BC. So we just see another example of how these problems, the problem of doubling the volume of the cube, trisecting the angle, and probably most importantly, finding the quadrature of a circle to find a square that has the same area as a circle, essentially finding a construction for the square root of pi. These 3 problems, for some reason, captured the imagination of the Greek geometers, and they went ahead and tried to solve these problems by hook or by crook. They abandoned the rules of Plato and went ahead as mathematicians and tried to use whatever mathematical ideas they could have to solve these problems. And here is just another example of creating new mathematics in the pursuit of solving one of these problems. Okay. And there, by the way, is the equation of the cissioid in analytic geometry. You can see not a particularly simple equation. But this was a great challenge to people like Fermat and Descartes as they begin to develop this idea of marrying equations to curves. They were given the curve. Here's the curve that Diocles gave, 1,800 years ago. Can I find an equation for this curve? This was the great challenge. And once they had that equation. Then as the calculus developed, could they turn that into some kind of a function of X or Y, and then apply the ideas of trying to find the tangent lines and the areas under these curves, and the arc length of the curve from one point to another. All the classic problems of early calculus were applied to these curves of the ancient Greeks. All right, I said we were going to do some calculus, so get ready. Let's do some calculus. Okay, we're going to take a look at a wonderful application of the derivative. And this is called Newton's method. Newton devised this method of using his idea of fluxions to find the roots of equations. And by no coincidence, let's go ahead and take the Delinean problem. Let's take the equation x cubed minus 2. Very nice function. I've graphed it for you there. X cubed minus 2. Notice what is the zero of that function? When is that equation equal to 0? What is the x that makes x cubed minus 2 0? Well, the cube root of 2. The cube root of 2 cubed minus 2 is 0. So that's this place right here. Okay, that's the cube root of 2 on this graph. Can we find that place? It's not. We can see it's an irrational number. It's a number of an infinite number of decimal places. Newton says, can we find an approximation to this number, to as many decimal places as we like? Okay. So we'll take just a little view of the genius of Newton. Let's see what he does. Okay, let's follow this argument. He says, well, let's take an arbitrary point. Okay, so let's take some point, we'll call it x1, and we'll look at f of x1. And we notice that no, x1 is not the right end. F of x1 is not 0. It's some negative number. So that's not the right number. So then he says, well, let's take the tangent line at x1. Let's go to our curve and take a tangent line and find where the tangent line hits the x-axis. Hits at some place called x2. x2 should be a better approximation to our cube root of 2 than x1. Now, it doesn't look quite so here. This looks kind of even further away than x1, but we'll see the logic here in a minute. So is x2 the right answer? Well, no. F of x2 is certainly not 0. Matter of fact, it seems to be a little bit bigger than f of x1. So let's keep going. Let's go ahead and take the tangent line at x2, f of x2. And we, of course, will find where the tangent line crosses the x-axis, and we get x3. Now it looks like Newton is onto something. Okay, x3 certainly is closer to our point than x1 and x2. If we do it again and take f of x3, notice that it, of course, is not exactly equal to 0. Take its tangent line and create x4. And we can see what Newton is doing there. Newton is claiming that if we continue this progression, we will get as close to the cube root of 2 as we like. We can generate this sequence of numbers, which will very quickly converge, using a modern word, to the cube root of 2. And the secret here is a very interesting one, a very important one in the idea of calculus. Why does this idea work? Newton says, well, you have to take a look at this point x3, x3, f of x3. Take a look at this tangent line. This tangent line is actually a very good approximation for the curve around its point. These points on the straight line are very, very close to the actual points on the curve. Not for very far, because here they drift away quite dramatically. But when you're in a close interval around x3, the straight line is a very good approximation of x cubed minus 2, the function x cubed minus 2. The fancy word for this is a linear approximation for the curve at these individual points. This is another one of the great applications of calculus, to use this idea that can use the tangent lines as approximations to our curves. Sometimes when you don't know what the curve is exactly, but you know its rate of change, and you can calculate the tangent line, you can actually use the tangent line for very close intervals around that for your curve that you don't know. Okay, and this leads to the whole area of approximations and numerical calculations, and things which engineers are forced to do in the real world because they can't find the exact solutions of things. So Newton is introducing a very, very powerful idea here, not just this method of finding the zeros of a function, the roots of an equation. By the way, those are just equivalent expressions. You could look upon this just as an equation, okay? And so we're setting this equation equal to 0. And what's the solution to that? That's called a root to the equation when you set the equation equal to 0. Or you can think of it as a function. And now I'm looking for the 0 of a function. I'm looking for that x, which makes the function 0. They are equivalent. So this is his idea. Okay, how does it work? Let's look behind this. Let's look behind this idea. And in order to do that, we really need to understand how we find these x2s and x3s and x4s. So that's the whole point. The whole point of this method is to generate this sequence of numbers getting closer and closer. How does he do this? So here's a wonderful opportunity finally for us to review the equation of a straight line, which is the one piece of algebra I warned you that we would do. Here we are, we finally reached it, so that we can understand Newton's method, so we can understand the power of the derivative in this one simple case, to show that it is the derivative that is doing this for us. Well, we can see the derivative is right here. We're looking at this, we're taking tangent lines. Okay, we're going to be using the slopes of tangent lines. Those are the derivatives. Okay, so let me take one slide with your permission and let us review the analytic geometry of a straight line. This is something, by the way, which Descartes never deigned to do. He was always working with much more complex curves using the analytic geometry we would hardly recognize. But Fermat actually would stop and show some of the elementary things of his ideas before he went back to working with his more complex curves that he was really interested in using this new idea of analytic geometry. So let us take some points that are on a straight line. Here are some arbitrary points on a line. And so here's our line. The idea is, how do we find the equation of the line if we're given some points? So let's go through it. We know the key to the problem is to find the slope of the line. Okay, that is the key to the problem. Here's our definition of slope. It's the change in y over the change in x. Let's take 2 points, any 2 points you like. Any 2 points will do. We can take 2 points that aren't even mentioned here. We can find 2 other points on the line. All the points will work. And let's go ahead and apply our equation for the slope. We can call this y1, call this point y2, and just plug in the numbers. You got to use your signs correctly. You got to be careful with the signs, your minuses and your minuses, the pluses, and all that good algebra. For you guys who are not up on your minuses and your minuses, don't worry about it. Take our word for it that we're doing the algebra correctly. We're applying the slope formula, the change in y and the change in x. That's what's important. And the algebra gives us a number of -3. We're certainly not surprised that the slope is a negative number. This line is going down, okay? Always we're looking to the right. We're looking as x gets larger and larger. What's happening to the y value? They're getting smaller and smaller. They're going down. So we're not surprised that the slope is a negative number. The algebra shows that it happens to be a -3. If you don't see that, if you don't want to go through all those minus signs, don't worry about it. That's technique. Okay, that's like pushing buttons on a calculator. It is not conceptually important how you go ahead and do that. All right, well, we got our slope, and so we know the slope formula, okay? The slope of this line, m, slope, is equal to the change in y of the change in x. Isn't that true for any points on the line? Any point xy, if I took any point xy and married it with the point x1, y1, a particular point on the line, and applied the slope formula, this equation would be true, that m is equal to any y minus y1 over any x over x2. But isn't that an equation in x and y? Isn't that the locus of an analytic geometry? Doesn't that make y dependent upon x? Isn't this an equation of analytic geometry? Okay. I just go ahead and take this equation, which has x and y as variables, and write it along the line. Okay, take that fractional part, take that denominator, x1 minus x2, and bring it upstairs over by the m, cross multiply. Again, for you guys who've forgotten your algebra, just trust me that this is valid algebra. All these equations are equivalent algebraically. And look what we have. We have an equation in x and y. It depends upon x1 and y1. It depends upon a point on the line, not surprisingly, and it depends upon the slope. But given any x, any arbitrary x I like, I can plug it into that equation and calculate y and get another equivalent point. I can create a table of values. This is an equation of a line. Okay? A very important one. It's called a point slope form of the line. Not surprisingly, because all you need is a point, x1, y1, and the slope, and you can immediately write down the equation of the line. So let's do that. There's our line. I simply take x1, y1 to be this point minus 1, 7. And so y minus 7 is equal to the slope minus 3 times x minus the minus 1. Clear up the algebra a little bit, and we have x minus 7 is equal to minus 3 times x plus 1. There is the equation of a line. It's simply the slope formula written along one line not in this fractional form. A very important form of the equation of a straight line. Oh, I could go ahead and solve that equation for y. That's not hard. Add a 7 to both sides and clear up the algebra, multiply the minus through. Okay, do some more elementary algebra, and we get right now y as a function of x. Y is equal to minus 3x plus 4. Another equivalent equation to all the ones up above. And this is another form. This is the second form of the straight line. This is the slope-intercept form. Because it turns out that, yes, the slope is still there, quite visible on the minus 3. That plus 4 is the y-intercept. Isn't that the place when x is 0? If you calculate f of 0, you'll get minus 3 times 0 plus 4. You will get 4. Okay? So 4 is, in fact, the place where the line crosses the y-axis when x is 0 at 4. So that's why it's called the slope-intercept form, because it's what's visible in the form is the slope and the y-intercept. Speaking of intercepts, we might as well go ahead and get the x-intercept, which we're interested in our Newton's method. We're interested in where these lines and curves cross the x-axis. What is the x that makes the value of the function 0? Set f of x equal to 0 and find the x that makes that true. Well, again, this is not a very difficult equation to solve. Minus 3x plus 4 is equal to 0. X is equal to 4/3. And then that would be where it crosses the x-axis. And that's everything we need to know about the straight line. We have two forms of the straight line, point slope and slope intercept. We can find the intercepts of the line. We know this. We can calculate the slope of the line. This is what we need to know about straight lines for the calculus. And this is what we need to know to understand Newton's method. Indulge me, guys, for a minute. The teacher in me, I can't help. Let's just do an example. Okay, indulge me. Here's another line, 2 different points. Let's find the equation of a line. Let's do another example. You always start with the slope. You find the slope, apply the formula, make sure that your minus signs are done carefully. And again, not surprisingly, we'll wind up with a negative slope, a slope of a negative 2/3. And we're done. We know the point slope form. And so we just say y, just take this point 3,2. A very nice point 3,2. So therefore y minus 2 is equal to the slope minus 2/3 times x minus 3. And that is the equation of a line. That's how easy it is using the point slope form. All you need to know is the minus 2/3 and the 0.23. You could have used the point minus 6/8 just as well. Would have given you algebraically exactly the same. We can go ahead and solve this equation for y. That's not difficult, and get the points, the slope intercept form. We could go ahead and calculate f of 0 to get the y-intercept of 4. Solve the equation f of x is equal to 0 to get the x where the function is 0, and we get 4/6. Okay, so there's just a nice example of what we did in the previous slide. Okay, I have another one for you. Okay, if you like a little homework problem, try this one. You'll find the answer to this. You'll find all the solutions to this on the last slide. Behind N, after N, you will find this slide again with the algebra done, if you're interested in trying it yourself before looking at my answer. Okay, let's go back to Newton's method. Okay, so for Newton's method, let's do this again. We're looking for this point here. All right. You may say, you know, what's the big deal? I can see that this point doesn't work. And so when we go ahead and take the tangent line, we'll get a line, another line, which Newton says this intercept should be better. Well, why don't we just go ahead and take this point here and move it, since clearly we're on the wrong side. Let's just take this point. Let's just take a succession of points getting closer and closer and closer. And these slopes will get up closer and closer. And eventually we'll hit the line. Well, you're not going to hit the line, guys. This is an irrational number. This line has an infinite decimal expansion. All that you can do, if you like, and if you like doing computations back in the 17th century, you could take a sequence of numbers, let's say a bunch of numbers. We don't know exactly what this point is. Okay, we do know that this point is bigger, so you could take an interval from here to here, for example, and divide this up into 10 equal points or 100 equal places, if you like, you know, and there's no calculator to help you, but the best you've got are logs, and you can go ahead and start making a calculation for each single point, find the tangent line, calculate the x-intercept, and see how you, and then check that intercept, cube that intercept, and see how you're getting closer and closer to the number 2. You could do that. Yeah. We'll see you in a couple of years when you're finished with that. Okay. What I'm saying is conceptually, we could do this because we do know, you know, conceptually that we are getting closer to, where am I here? We are getting closer to, the tangent is getting closer to that line as we get closer and closer to that point. Okay, here I've taken a point beyond, I've taken the point 2. Here's our point. And as we move closer and closer, we are going to get an intercept closer and closer to the one we're looking for. Yes, we will do this. But the only way to do this is to take these successive points getting closer and closer. Okay, and Mathematica can do it very, very quickly. Okay, back in the 1700s, the 1600s, you can't do this quickly. What Newton is finding is a progression. He's finding an algorithm which we can follow, which will get to this point in like 4 steps by using his idea of the derivative. Okay, that's what we want to show. All right, so let's go ahead and show it. All right, we'll try this again. Same curve, same idea. We start with the same point, x1. We go ahead and find this point x2. I'm sorry, we find the line. Okay, here's our line. Our line is y minus f of x1 is equal to m times x minus x minus x1. Okay, and we have a point. The point here on this line, on this tangent line, is x1 f of x1. So here's our point, x1 f of x1. I'm using the point slope form, and I have my slope m. But we know what m is. M is f prime of x1. It's the derivative of the curve at x1. Look what the equation of our line is. The equation of our tangent line is completely and solely dependent upon the point x1. As soon as you give me x1, I can immediately write down the full equation of the line. I need to know the y value at x1, I need to know the x value at x1, and I need to know the derivative at x1. It gives me all the 3 pieces of my point slope form. Well, now that I have the equation of the line, I certainly can find the x-intercept of the line. I certainly can find out when that line crosses the x-axis. I can certainly find out when the y value is 0. Just take my equation and make y 0 and solve for x2. By making y 0 the solution to this equation, x now becomes x2. My unknown is now the place where y is 0. The place where y is 0 is on the x-axis. I can go ahead and solve this equation for x2. A couple of steps, a couple of swishes and swashes, a couple of things on both sides. Again, for you non-algebraists, don't worry about the algebra. take my word for it. The people who are remember their algebra well, you can see what we're doing here is very, very simple algebra. And there's x2. Not only is the tangent line completely dependent upon x1, we're not surprised that x2 is completely and solely dependent upon x1. I get x2 immediately from x1. As soon as I know x1, I can go ahead and calculate the derivative of x1 here. I can calculate the functional value of x1 here, and I can immediately write down the value of x2. Okay. And I can do it again. I can go ahead and take that point, draw the line, find x3. Take a wild guess what x3 is. Take a wild guess. Yeah, x3 has exactly the same form as x2, except x2 needs x1, x3 only needs x2 in exactly this, because the mathematics is exactly the same. The reasoning is exactly the same. And to find x4, when we're really beginning to hone in here, yeah, I don't think you're surprised that x4 has the same relationship to x3. And you can see how yes, we can generate, these are calculations that have to be done, but there are Newton has reduced them down to the minimum, and they are very straightforward. The calculations are being done in the same way over and over again. And we just keep doing this until we're satisfied that the f of x4 is very, very close to the number 2, that when we cube x4, we get a number of 1.997, and we're happy, and we found our function. Okay, so this is Newton's method, a very, very nice application of the derivative. Okay, but remember, the idea behind it is even more profound. What Newton is saying is realize that what you have here in the tangent line, okay, something that the Greeks never had to appreciate, didn't have to worry about, because they didn't have the idea of a function. But as you have the idea of a general function, the tangent line serves a very important purpose. The tangent line is a very good approximation of the curve around its tangent point. And you can actually use it in many scientific and engineering applications as a proxy for the line, as long as you stay close, a close interval around that tangent point, x4. Okay. And if we were to draw the tangent line at x4, I didn't want to muddy the picture so well. We'll let Mathematica muddy the picture. That it does a better job. As we do this, we can see how that tangent line is certainly starting to lay right over right over the point of interest. Let me just do the animation, and then we'll stop and we'll take some questions. I think you'll like this. Okay, so here is Newton's method. A little bit of a different interface here. What I'm doing here is I've drawn this quite arbitrarily so we can have some fun. If someone has a calculator, a scientific calculator that can take square roots and cube roots, I really appreciate you getting that calculator out and confirming the numbers that Newton's method shows. So I have my equation, y is equal to x to the n minus k. Notice our example is x cubed minus 2. Okay, the particular example we took was x cubed minus 2. So that's what I'm starting with. I'm letting n be 3, I'm letting k be 2, and we're starting with the number 1. This is exactly the scenario that we just did in the PowerPoint. So I have my equation x cubed minus 2, and I want to start at 1. So let's see what the animation shows. I'm going to do this in steps, each step finding x1, the next 2, and the next 3, using Newton's method. I have the steps up here in the table. I'm going to start with 1. Okay, what's the next step? I'm going to get the x-intercept. That x-intercept is right here. It's 1 1/3. Well, let's take now 1 1/3. Let's use that as our next point. Let's go the next step. Here I am now at 1 1/3. Let's draw the x-intercept. I've got this point here. Now at 1.263. I'm very, very close. Well, let's keep going. Let's take the next step. I'm practically on top of it. Here I am at step 3, I'm at 1.26389, okay? And the next step here, and in terms of the picture, I'm on top of this thing, okay? Here at step 4, I'm at 1.25993. And notice the steps do not change, okay? I do not get a better approximation. In 5 decimal places. If I was writing this thing out to 10 decimal, if I asked Mathematica to write this out to 10 decimal places, I would be getting better and better approximations. But 1.25992 is not, is a pretty good approximation. Does anybody have a calculator that they can cube 1.25992, multiply 1.25992 times itself, and then take that number and multiply it by 1.25992. Multiply that number 3 times. Is anybody out there who can do that? I'll take that as a no. No one can do that? All right. Well, let's
Somebody can ask Google.
okay. Let's go ahead and take a number that we do know. Let's take the square root of 2. The square root of 2, I think, is a number that we'll recognize. And so what do I need here? I need to take the square root. I want n to be 2. Okay, let's take the square root of 2. And let's also start at 1. One's a good place. Square root of 2 is 1.41. I kind of recognize the square root of 2. Okay. So here we have x cubed minus 2. Here's our curve. Here's our first point here at 1. Here's our first point at 1. Wait, what do I got here? I'm sorry, guys. We're at this. Let me try this again. Did I do this wrong? Let me see. 2. I know what I did wrong. Okay. I think I know what I did wrong. Let's see if this works. Hope I don't have a bug in my program. It's been known to happen before. Okay. I think I entered in the numbers wrong. Okay. Take a look at the answer. The answer is 1.414. I think many of you recognize that as a square root of 2. So here I started at 1, and we go through our steps. We wound up at 1.5. Here's 1.5. 1.5 will give me a new x-intercept at 1.41667. I go to the next step, and there I am. I'm at 1.422. One more will give me 1.421. And after that, in terms of 5 decimal places, it stops. Anyone take a regular calculator with just a decimal point? Can you take 1.41421 and multiply it by 1.4121? Just multiply that number by itself. Can someone do that and give us a number? Nobody has their phone with a calculator in it?
Yeah, you get 2.
Okay, thank you. Newton's method works. I was just looking for a verification. Let's do one more, just for fun. Let's go ahead and find the square root of pi. Isn't that the answer to I don't have my palette up. That's not good. What happened to my palette? Oh yeah. Can I bring this thing down? Okay. Let's do this one more time, guys. Let's find the square root of pi, because that's what they were looking for. I seem to be hung here. Hold on. I think I've done something that has made Mathematica mad. And we seem to be hung. All right, I apologize for that. This does happen with a very complex program like this. And let me get out of it. Yeah, it's okay, let's try this one. Let's try once more to find the square root of pi. If you have a pi on your calculator, if you can get ready for this, to take the square root of pi. Pi, of course, is 3.141, et cetera, et cetera.
I have it.
Let's try Newton's method on the square root of pi. Here we go. Down here, let's run this thing. Okay. Okay, so I want to take the square root of pi. I'm going to choose, that's why I wanted the palette. I want to choose Mathematica's value of pi. So it's a nice exact number. And again, the square root of 3 is about 1. So 1 really works just fine. Actually, I think I'm cheating. Let's take 2. Let's go beyond the square root of pi to show that Newton's method does not care as long as you pick a point somewhere around there. So again, the equation I have is x to the n minus k. So I have x squared minus pi. So the root I'm looking for is the square root of pi, which is what is the doubling of the cube problem. Okay, looks good. Here's our graph. Oops, sorry. Here's the graph of the equation x squared minus pi, and I've taken the number 2. Okay, so I've taken a point beyond the value. Newton's method doesn't care. And we see the steps. Very much coagulate to 1.77245. You start with the number 2. The next point we'll get is this point here, which is 1.7854. There's 1.7854. We go ahead and do the method again, and notice that mathematically we're on top of ourselves in terms of I would have to really expand this thing to see the difference. The number here that Newton gives us is 1.77245. Can you square 1.77245? What do we get on the calculator? Anybody?
3.14159.
Oh, I'm sorry, what do you get?
Oh, you got pi, 3.14159.
Okay, thank you. All right. Just wanted to show everybody that Newton knew what he was doing, in case you didn't believe him. So, all right, I think the point is made. It's a very, very powerful method. You can see with my interface, okay, just look at that one more time. We could put in any n that we like. We can put in any number k that we like. We could find the 5th root of any number that you like. And this, of course, has nothing to do with squares and cubes. We can take any function and apply Newton's method and use this idea of this iteration, and you will get very, very quickly, you will. So when you're using your calculator, guys, who just read us off, value of pi, the value of these roots, what's programmed inside that calculator more times than not is Newton's method. That's what the calculator is doing to come up with the square root of pi. All right, very good. Let's get out of this and move on. So I think this is our first application of the calculus. Are there any questions about what we've done here?
I have one, Peter. This is Sharon.
Yes.
So being totally ignorant of the historical context, did Newton have the benefit of all the Euclidean work when he did this?
Oh, yes. Oh, my gosh. Oh,
So
my gosh.
that's what made him think about how to do this. He didn't just magically
Oh,
go
gosh.
off.
Now, remember, Newton's Principia is filled with, it's all written in Euclidean geometry. He used actually very little calculus in it because he didn't want to use the calculus because people didn't know what he was doing in the first place. Never mind using his new calculus. Newton was, Newton was an expert in all the mathematics of his day. He invented half of it. So yes, he knew all of Euclid and Archimedes and Apollonius and Descartes and Fermat, and he knew all of the mathematics that came before him. Okay, and so we're looking at a progression. The analytic geometry that we're using here, equations of straight lines, is all done 50 years before Newton in the work of Descartes and Fermat. I have a story I must tell you, not that you need the benefit of it, but it was a favorite story I would like to tell my students, my high school students. Newton describes how he learned Descartes' geometry. Remember, the geometry was an appendix to the Discourse on Method, the famous "I think, therefore I am" philosophical tract. He wrote 3 appendices to that document, and one of them was his geometry. Newton says, I found the geometry of Descartes very difficult to understand. So what I did was I began reading from the first page, and I would read and I would read and read until I didn't understand what was happening anymore, when I couldn't follow what he was doing. And what I would do then is I would go back to page 1 and start reading again. And I found that I could get further the next time than the first time, but very often I would get stuck again. And I got to a point where I didn't follow what he was doing. And what I would do is I would go back again to the first page and start again. This is exactly what he says in his writings to describe his study of Descartes' geometry. And I would say to my students, guys, if it's good enough for Newton, it should be good enough for us, okay? If you don't understand something in the textbook, first of all, don't be afraid to read the textbooks. We all know students don't read their math textbooks. I've never figured out why. They only use it to look at their homework problems. Read your textbook, you'd be surprised, it's all there. And if you don't understand something, take a page out of Newton and go back to the beginning of the chapter and start reading again. So it's a great anecdote that I used in my teaching. Okay, so let us move on to the next idea in the history of calculus from the Greeks, and we're still with Diocles. Diocles proved a very interesting property of the parabola. He was interested in a parabolic surface, and what would happen if you thought of drawing a line down to the parabola, and then drawing another line to the focus. Notice I don't have any X and Y's here. We're working in Greek geometry, but we do allow to have a axis line, and we certainly have a vertex of the parabola. What he was able to prove was that if you drew the tangent line at that point, which of course his older teacher, Apollonius, showed him how to draw the tangent line to the point. What Diocles proved was that these 2 angles were equal. So if you draw a line parallel to the axis and then draw to any point on the parabola, draw another line then to the focus from that point, and then draw the tangent line, these 2 angles that those 2 lines make with the tangent line are equal. And this is exactly reminiscent of the law of reflection. This is what would happen if the tangent line was a mirror. If it were a straight mirror, this is how a ray of light would behave. And this was well known to the Greeks. This property of light was well known before this time. Euclid knew this 100 years before this. But he was able to prove this theorem. And since light is irreversible, since light is reversible, any path that light takes, it will also take the opposite path going back the other way. And so, I'm sorry, just to finish the idea, if you were to take the line perpendicular to the tangent line, these 2 angles would also be equal just from the geometry. And in optics, actually, these are the angles that you deal with in the law of reflection. For straight mirrors, it doesn't make any difference. It's all equivalent. So we want to work with the angles right from the tangent line as opposed to the normal line. It's just easier for us to think about. I don't even know why I put that in. I shouldn't have put in that equivalence. The point I want to make, though, is since the path of light is reversible, it should be the case if you draw any line from the focus to any point on the parabola, it should, whoops, I'm sorry, it should bounce off parallel to the axis of the parabola. This should be the case. And in fact, if you were to take the tangent line here, these two angles would be equal. This is a very interesting situation, Gus. What you're looking at here is the telescope. This is why telescopes all have parabolic mirrors. This is why the telescope that's up in the Webb telescope that was just put up there a few months ago has a parabolic mirror, just like the Hubble telescope, just like all the great mirror telescopes on Earth, like the Keck in Hawaii. They all have parabolic mirrors because the light being gathered from the stars so far away they're so far away, the light is parallel. And so all the light comes in and is all gathered at the focus. And this is why our headlights for our car headlights are parabolic mirrors, because when you put the bulb here at the focus, all the light coming from the focus will go straight out parallel in one direction and you get a directed beam. Okay, so this is the application of a parabolic segment. Okay, remember what a parabolic segment is. You just go ahead and take this line and revolve the parabola around this line as a volume of revolution. Okay, the stuff that Archimedes was doing. Okay, so let me show you that animation of the focus property of the parabola. So no matter how the light comes in, it'll always make an equal angle. No matter what angle it comes in, the light behaves as it, the surface that it's hitting, although the surface is curved, it behaves as if it is hitting a surface that is straight. What straight? Not surprised, the tangent line. Because isn't the tangent line capturing at that place, at that very, very close place? This is what Newton is getting after, that the tangent line is the proxy for the curved line at the place around that point. You can't get any closer to the point itself. So what does the light think it's hitting? The light thinks the light is behaving as if it is hitting a straight line. What straight line? The tangent line. And so this proof of Diocles, this behavior of light, is a wonderful example of what Newton is talking about, that the tangent line is exactly the proxy for any curved line at an interval very close around the tangent point. Okay, and all I'm showing here are the equal angles. These are just the angles in degrees that we're showing here, even the 90-degree angle. Okay, at that point. So a very nice theorem of Diocles, which again is an important idea. And also, I wanted to show you another example of the tangent line. Again, answering that question, what's with the tangent line? Why are these Greek geometers interested in tangent lines? Well, here's just another reason. Okay, a very nice, Apollonius is finding how to find tangent lines. Well, okay, that's a purely mathematical thing. Here's now the next level. The next level is, okay, let's take a look at what tangent lines can do for us. And here's a wonderful theorem about parabolas and tangent lines, and the nice application for parabolic mirrors. Okay, this idea of bouncing light off of curves became very interesting to our scientists and mathematicians of the Renaissance. Once they had this idea, they said, well, this idea of the tangent line acting as the straight surface for a beam of light at any point, let's take any arbitrary point on another conic section. For example, here for the ellipse, let's go ahead and take a point and let's just direct a beam of light to another side of the ellipse. Let's imagine that we have a tangent. We've drawn a tangent line here. Okay, we've drawn our tangent line here. And how is this light going to bounce off? It's going to bounce off following the law of reflection. If you can mention, I didn't want to mussy up the picture with all these lines, so I have something prettier to show you. if you can see in your mind's eye, if this is the tangent line, that these two angles would be equal, okay? And so this light, it just bounces along, following the law of reflection. Well, this became an interesting question to people like Fermat and Descartes and the other mathematicians who came beyond them, using the analytic geometry of finding these tangent lines and how they bounce. And look what happens if you just follow this. You get what mathematicians call an envelope. You get a series of lines, a family of lines, and what we've created here, it's kind of a ghost. What we created here is another ellipse, okay? This ellipse is called an envelope of this family of lines. The envelope of a family of curves is defined to be another curve which is tangent to every line in the family. I'm sorry, to every curve in the family, because these curves don't have to be lines. Here, our example, our family is a family of lines. Fine. The more general thing is you could have a family of any curves, and I'll show you some next week. But here we have a family of curves, and the definition of an envelope is another curve which is tangent to every single curve of your family. And the ellipse here, this phantom ellipse that the lines have created, is that envelope. This became a whole study in the 17th century to see how families of different kinds of curves, lines, circles, different conic sections, how families of these curves could they create envelopes, and what kind of envelopes would they create, and could the analytic geometry / calculus find what the equation of these envelopes were. And we'll see, I'll show you a little bit of this next week when we look further at the derivative. But I just wanted to give you one example of it coming from this idea of the reflection of beams of light, a particular case of that. Okay. We move on to our next mathematician in the history of calculus. And I think we'll stop here, but this is a very important one. This is for the first time in the history of mathematics and science that we are able to derive a law of motion, a law of nature from another mathematical principle. We'll see what I mean in a minute. We have a law of nature, the law of reflection. The law of reflection says that if you have a ray of light, this is a mirror. You take a source of light, have a ray of light, you hit that mirror. Where does it bounce off? Where does your eye have to be to see this ray here at A? Where will be the path of light? Euclid knew that the path of light was such that these two angles were equal. This is the law of reflection, okay? This is a known law, that this path will be created such that these two angles are equal. Remember the name of Heron, about 100 years, I think about 100 years after Diocles, went ahead and proved the law of reflection from a more fundamental mathematical law. And this will become very, very important in the whole idea of mathematics and find its home originally in the calculus. So let us take us through what Heron is about to prove, and then we'll see its wider implications. What Heron is going to prove is that the reason why the law of reflection is true is because this path is the path of least distance. Of all the paths that this thing could take from the mirror, from A down to B, take a path from here to B, of all the various paths, this is the one that makes angle 1 equal to angle 3. This is the one which is the shortest. And that's why the light behaves that way, because nature wants to take the shortest path. And this is a very powerful idea, that nature works in some kind of a maximum or minimum way. And this is just as true today in studying quantum physics and particle physics and and cosmology, nature seems to follow this basic idea. Heron is the first one to see this and to prove this. So let's go ahead and go through the proof. It is a wonderful geometric proof using a Euclidean geometry. So let's state the theorem. If the path from A to R to B is of the least distance, if it is, then angle 1 is equal to angle 3. That is, if the path is the least distance, then you have the law of reflection. The law of reflection is created from, it is a consequence of, it is derived from this minimum distance law. There's something behind the law of reflection. There's something more fundamental than the law of reflection, which is causing it to be so. That light wants to take the path of least distance. Okay, let's look at the proof. Let's consider any other path. Let's take a point P, and let's look at that path. I think we'll agree that that's a longer path, but we'll prove that. Okay. Heron says, take the point A1 exactly down below the mirror, exactly equal distance. From A to M, M to A1 is the same. Now let's look at that path. Let's look at the path from A1 to P to B. It's a nice path. Take a look at these two triangles here. Triangle 1, nice right triangle, and triangle 2, where P is the vertex. We can see that these two triangles are congruent. Okay? Remember the fundamental congruence relationship, side, angle, side? Yeah, SAS, you remember that. Someplace back in your brain, you remember side, angle, sine for the congruence of triangles. This is a right triangle, two right triangles, where these two sides are the same. We made it so. They're right angles, and of course, this is the common side. So we have side, angle, side. These two triangles are congruent, and therefore these two lengths are equal, their corresponding sides. So AB is the same as A1P. We say that again. AP is the same as A1P. Okay, well now look at this distance, A1 to P to B. This is the same distance as A to P to B, because this is the same distance as this. They both have this distance in common. So to get from here to here to here is exactly the same as to get from here to here to here, because these two lines are equal, because these two triangles are congruent. Are you with me? Okay. Therefore, what is the shortest distance? This clearly is not the shortest distance from A1 to P. The shortest distance from A1 to P is the straight line from A1 to P. Find the place where the straight line crosses the mirror. Call that place R. This clearly is the shortest distance, because the shortest distance from A1 to P is the straight line. Since this is the shortest distance from A1 to the mirror here, it's therefore the shortest distance from A1 to R to P. It must be. Let's take away these lines, they're confusing. Let's go back to this triangle. Now with the vertex at R, this again, we have another set of congruent triangles for the same reason, angle, side, angle. AR is equal to A1R, and therefore the distance from A1 to R to B is the same as A1 to R to B, but we've agreed that A1R to B is the shortest distance from A1 to B, and therefore this is the place to give us the shortest distance from A to R to B. The proof is almost done, guys. If these two triangles are congruent, not only are these two sides equal, but these two angles are equal. They're corresponding angles. Angle 1 is equal to angle 2. But isn't angle 2 equal to angle 3? And here's the key point. Why is angle 2 equal to angle 3? Because these are vertical angles. Why are these vertical angles? Because this is a straight line. If this were not constructed as a straight line, you could not say that angle 2 is equal to angle 3. Because we've constructed the straight line all the way through, and we've made R that place where A1B crosses the mirror, this is a straight line, and therefore these are vertical angles. So 1 is equal to 2, 3 is equal to 2, and therefore 1 is equal to 3. Okay. This is the first extremum theorem in the history of math and physics. Fermat will go along and prove the law of refraction in the same way using his primitive calculus. Okay?
Peter,
He will
excuse me a second. What was
Yes.
that phrase you used for the theorem? You had a word before
It's,
it?
it's an example of an extrema theorem. It shows that nature follows some kind of an extreme course, either a maximum course or a minimum course. And we find examples in nature where they will do both. Okay, here's an example of a minimum course where the trip is of the shortest distance. By the way, notice that it's also of the shortest time. Since everything is traveling here in air, presumably here hitting a mirror, this is also the shortest time to get from A to the mirror to B. Okay, that's just a consequence that the thing is moving always at a constant speed. Fermat's going to come along 1800 years later and show the law of refraction, where we go from air to water to air, that path is the shortest time, that the law of refraction, if you remember Snell's law, if you don't remember, it's a law of how things bend. He shows that the way the bend is, the law that we know in nature, the way it has that bend is because the angles must be such that the path gives us the shortest time, given the different speeds going through air and water. This is the second example of an extrema thing. And it is right in the teeth of his elementary calculus. But it begins here with Heron's formula. And it's nice to show this theorem because it only uses elementary geometry. Right? The only theorems I'm using here are right from Euclid. Okay, let me just show you the animation and we'll call it a day. What Heron is saying is, of all the places P that you pick any place P that you pick, and you'll get these different angles. The place where the angle is equal, that's going to be the shortest. Here, this angle is bigger than this angle. This is a longer distance. This place here, the angles are not equal. This is a longer distance than this distance here. Where's the shortest distance? The shortest distance is when the black angle is equal to the blue angle. That's when you're going to get the shortest distance. That's when you're going to have the law of reflection. Okay, guys, so why don't we stop there?
Peter, so
Yes.
you've given two examples here of nature following the most direct course or minimal
Yes.
course.
Yes.
Can you give an example of a maximal course, which you said is the other, could also be an extrema theorem?
That is a damn good question. I can't think of one offhand. You've given me my homework for next Thursday. Okay, if either next Thursday or by Tuesday's email, let me answer that question. It's a wonderful question. Who's asking that question?
Carl Sherman.
Oh, okay, great question, Carl. Great question. All right, are there any questions other than Carl's question, which is a stumper?
This is Antonia, and I have one trying to put things that might be not meant to go together. This point R, the reflection point, the light hits R and then it leaves R. So A to R, R to B, correct?
Correct.
And that doesn't hang around on point R. This is instantaneous, but can we even agree that there's such a thing as instantaneous? And it made me think of the very first, I think the first video, and there was the woman in the roller coaster, and we were discussing speed, and you shared.
Antonia, what you're doing here is you're overthinking the problem. We're just talking about a ray of light. The ray leaves this lamp at A, like a laser pointer. We shine it down to the mirror and it bounces off the mirror to go someplace else. That's all. It's a ray of light that bounces off of the mirror. We're not talking about the motion of the particles of light or anything like that. It's just the path that the laser beam takes. in its
Okay.
travels. Okay?
Thank you.
You're overthinking the problem. You're turning it into a motion problem, which it is not, okay? Any other thoughts or any questions about anything that we've talked about in this class? Okay, guys, I'll take that as a no. We'll finish off this presentation and we'll start our derivative presentation for our last class, and we'll see how far we get. All right, guys, I'll sign off until next time. Have a good day, guys.